Welcome back to the deep dive. Today we are tackling something that I think is arguably the most universal struggle of modern life.
Oh, yeah.
I mean, I'm talking about the invisible force field that we all completely depend on, but none of us actually understand.
You are talking about Wi-Fi.
I am talking about Wi-Fi, specifically that rage-inducing moment when you're walking from the kitchen to the living room and suddenly
Everything just stops.
right, your music stops or your video buffers and you're just standing there holding your phone in the air like the Lion King.
Trying to find the signal.
Exactly, just wondering why it works in one spot and literally 2 feet away it doesn't. You start thinking, is my router broken? Is the internet down? Am I broken?
Usually it is not you that's broken.
Good to know.
But the way we understand wireless networks is often a bit, say, optimistic.
Optimistic how?
Well, we look at the little bars on the phone.
Right.
And if there are 3 bars, we just assume everything should be perfect.
Right, because full bars means fast internet. That's what we're taught.
Exactly. But under the hood, it is actually a chaotic, noisy mess of radio waves.
Which is exactly why today is going to be so satisfying. We are stripping away all that marketing fluff.
No spaceship routers today.
Nope. We aren't looking at some shiny brochure for a $500 router. We're looking at a technical blog post from a self-described old software plumber.
His name is Kian Meng Ang.
Yes, and he is the perfect kind of source for this.
Completely. Because this isn't someone trying to sell you a monthly subscription or a fancy mesh system. This is a guy who just likes tinkering with the pipes.
The digital pipes.
Right, to see how the water is actually flowing. He's looking at the raw data.
And the topic on the table today is Wi-Fi 7.
Also known by its very catchy robotic name, 802.11b.
Naturally. But the twist here is that we aren't just doing the usual tech review thing and talking about faster speeds.
Then we're talking about a fundamental shift in how our devices actually talk to the router.
Right. So the mission for this deep dive is to demystify those cryptic numbers that show up when you actually pull back the curtain on network performance.
We want to move past just asking, is it fast?
Because fast isn't the whole story.
Not at all.
Yeah.
We need to start asking, is the connection healthy?
And to do that, we really have to talk about the star of the show here, a little concept called MLO.
Multi-link operation.
Yeah, break that down for us because this seems huge.
This is the absolute game changer for Wi-Fi 7.
Yeah.
So in previous versions of Wi-Fi, like Wi-Fi 5 or Wi-Fi 6, your phone or your laptop basically had to pick a lane.
Okay.
It was either on 2.4 gigahertz, which is, it's slow, but it travels really far. Or it was on 5 gigahertz, which is fast, but has a really short range.
So it made a choice, one or the other.
Exactly. But MLO effectively comes in and says, well, why choose?
Why not both?
Right. It allows a client device to connect to the router across multiple bands simultaneously.
So it's kind of like having a conversation with someone on 2 phones at the exact same time just to make sure you don't miss a single word.
That's a great way to think of it. Or like driving a car that can somehow use 2 lanes of the highway at the same time to get around traffic.
That sounds incredibly efficient.
It is. It massively increases reliability and throughput. And in the source material we're looking at today, our software plumber actually takes us through a real-world, hands-on analysis of what MLO looks like.
When you look at the raw data.
Right, when you peel back the user interface on a Linux machine.
Okay, so let's set the scene for this test because context is everything here. Our source is not in some pristine lab environment with copper-shielded walls, right?
It's a very relatable setup, actually. The router is sitting on the ground floor.
Okay.
And the Wi-Fi adapter, so the client that's trying to get online is up on the 2nd floor.
Oh, wow. So that is the classic dead zone recipe right there.
It really is.
Floor separation, you've got wood, maybe concrete plumbing pipes, electrical wiring.
It's an absolute obstacle course for radio waves.
But we'll see that in this case, the results are surprisingly robust. Now, to get these results, he didn't just click the little Wi-Fi fan icon in the corner of his screen.
No, he used a command line tool called IO. Just 2 letters, IW.
Short and simple. Is this something anyone listening can just use?
If you run Linux, yes. It's the successor to the old iConfig tool for anyone who maybe messed around with Linux back in the day.
Oh, I remember iConfig.
Yeah, so Icon talks directly to the NLA02A1 interface.
Okay, wait, let's unpack that jargon for a second. NL802LM.
Think of it as a bridge. On one side, you have the user typing commands into the terminal, and on the other side, you have the actual hardware.
The physical chip.
Right, the wireless driver, which in his specific case is the MT7925E.
Catchy names all around today.
Very catchy. So NLA0201 is basically the translator that lets the software ask the hardware Hey, don't show me the pretty user interface version.
Tell me what's actually happening.
Exactly. Tell me what you are doing right now physically.
And when he asked the hardware that question, the first thing that jumped out in log was the signal strength.
Yeah, he recorded a signal level of -63 dBrem.
Okay, now I know usually when we talk about decibels, closer to 0 is better, but these negative numbers are always a bit tricky for me. Is -63 good?
It is surprisingly good, especially for a second-floor connection.
Really?
Yeah, so in the world of Wi-Fi, 0 is theoretically impossible unless your device is literally plugged into the router's antenna.
Okay.
-30 DRAM is like standing right next to the router in the same room. -90 DRAM is basically completely unusable. The background noise just drowns out the signal.
So -63 is kind of right in the middle.
It's solid. It is a very healthy, highly usable signal.
But wait, he's on the second floor. You said earlier floors kill Wi-Fi. How is he getting -63?
Well, the source notes a really important physical detail here that completely changes the physics of the situation.
What's that?
There is an open door nearby.
An open door. The low-tech solution to a high-tech problem.
Exactly. I know it sounds silly, but radio waves at these frequencies, at 2.4 and 5 gigahertz, they behave a lot like light.
They bounce.
They bounce.
Yeah.
If you close that door, the signal literally has to punch its way through the floorboards and the joists, and you lose a massive amount of energy doing that.
But with the door open.
With the door open, the signal can just travel up the stairwell, bounce off the landing, and flood right into the room.
Wow. So it's a good reminder that before you go out and buy a $500 mesh network system, maybe just try propping a door open.
It is honestly the cheapest signal booster you will ever find.
So the signal is strong. Now let's look at this MLO thing, the multi-link operation. When he runs that iTool, the output looks completely different than older Wi-Fi versions.
Right, because he sees two distinct links active at the exact same time.
Link 0 and link 1.
Yes. This is the visual proof of MLO working. Link 0 is connected to the 2.4 gigahertz band, and link 1 is on the 5 gigahertz band.
Both active simultaneously.
Both active.
But here's where the detective work kind of starts in the post. Because the tool doesn't just nicely say, oh, you are on channel 6.
That would be too easy.
Right. He gives a frequency in megahertz. And our source has to do some actual math to figure out where he is connected.
It's a bit of retro math. For the 2.4 gigahertz band, he sees 462.0 megahertz.
Okay.
Now, Wi-Fi channels in that specific band are spaced exactly 5 megahertz apart.
So if you know where channel 1 starts.
Just 2,412 megahertz. You can just count up.
Okay, so 2 4 12 is channel 1, 2 R 17 is channel 2, and eventually you land on 2062.
Which is channel 6. Precisely.
Simple arithmetic. But the 5 gigahertz band connection seems a little more calculated on his part.
It is. Based on the frequency he sees there, he deduces he is on channel 40. And this is where it gets really, really interesting for anyone trying to optimize their home network.
Okay, why? What is so special about channel 30?
Channel 40 sits in a block called the UNII-1 band.
UNI-1? That sounds like a sci-fi faction.
I know. It stands for Unlicensed National Information Infrastructure.
Say that 5 times fast.
I'd rather not. But here is the big takeaway for you listening at home. UNII-1 channels, specifically channels 36 through 48,
Yeah.
that do not require DFS.
DFS. That sounds like a government agency.
Close, actually. It stands for Dynamic Frequency Selection.
Okay, what does that mean in plain English?
So here is the dirty little secret of 5 gigahertz Wi-Fi. A huge chunk of the channels we use at home are actually legally shared with weather radar and military radar systems.
Wait, really? My router shares space with the military.
Yes. And if your router detects a radar ping on its channel, it is legally required to shut up and move to a different channel immediately.
Oh, wow.
It has a mechanism called listen before talk.
So that is why sometimes my 5 gigahertz connection just drops or vanishes for a minute. It's dodging a Weber radar.
Exactly. It could be a plane, a weather balloon, or honestly just a false positive from a microwave. But your router drops everything to change lanes.
That's incredibly frustrating.
But channel 40 doesn't have that requirement.
Because it's a non-DFS channel.
Right. It doesn't have to listen for radar. It can just broadcast constantly. So it is often a significantly cleaner, more stable choice for indoor Wi-Fi because it doesn't get those sudden interruptions.
So if you can log into your router and force it to the lower channels like 36 or 40, you might actually get a much more stable experience.
It's highly likely, yes. Stability often trumps raw speed in these setups.
Speaking of speed, let's talk about the numbers that literally everyone obsesses over.
Byte rates.
Yeah, the source records at bitrate, and the download and upload rate is showing us 432.3 megabits per second.
432.3 megabits fast.
Now, if you look at your screen and saw that number, you'd probably think, great, my internet is 432 megabits fast.
Naturally, I'd be thrilled. I'd think I'm downloading a movie in 10 seconds.
So that would be a mistake.
Why?
Qian Meng uses a perfect analogy here. That number, that link speed, is just the speed limit of the highway.
Okay, let's unpack this. The speed limit versus the speed of the car. Right. The connection between your computer on the second floor and the router on the first floor has established that it could technically handle traffic moving at 432 megabits per second.
That's the physical capacity of the road.
Exactly. But that absolutely does not mean the car is actually moving that fast.
Because of the internet provider. Like if I only pay for a 100 megabit plan.
That is one major bottleneck.
Yes.
If you only pay for 100 megabits, it doesn't matter if your local Wi-Fi highway supports 400, you are capped at the on-ramp to the wider internet.
Makes sense.
But there's something else too. Something entirely local. The Wi-Fi tax?
The Wi-Fi tax. Great. I feel like I pay enough taxes in real life. What is this one?
It is the overhead. It's the management traffic.
Management traffic.
Yeah, in Wi-Fi, roughly 30 to 50% of that link speed is just completely eaten up by the protocol itself.
Wait, 50% doing what?
It's the network talking to itself.
Yeah.
Saying things like, did you get that packet? Yes, I got it.
Okay.
If you're setting the next one, wait, let me verify the checksum. All of that takes up space on the road.
So if my link speed says 400, I'm really only getting, what, 200? Maybe 250.
Realistically, yes. If you ran a proper local speed test like iPro 3, you would never see 432. You'd see significantly less because of all that management overhead.
That honestly feels a little like false advertising by the router companies.
It's just the physics and the necessary protocols of wireless communication. But here is the important context the source brings up. Is 432 megabits link speed actually enough?
Well, is it? Because it sounds kind of mid-range compared to the gigabit and multi-gigabit promises on the box you buy at the store.
It is absolutely enough. Even with the 50% tax, you still have hundreds of megabits of actual throughput.
Okay.
A 4K Netflix stream uses maybe 25 megabits.
Oh, wow.
Yeah, you can stream multiple 4K movies simultaneously on that specific connection without a single hiccup. The local network here is just not the bottleneck.
So the takeaway here is stop obsessing over getting the number to 1,000 if 400 does the job perfectly fine.
Precisely. You don't need a Ferrari to go to the grocery store.
Now, part of the reason this connection is working so well on the second floor is how the engine is tuned.
The router settings.
Yeah, the source mentions he tweaked the settings and landed on a channel width of 80 megahertz.
This is a really critical setting. Most modern routers let you choose your channel width. 20, 40, 80, or even 160 and 320 megahertz in the newer Wi-Fi 7 standards.
Right. And usually in the tech world, the bigger the number, the better the performance. So why wouldn't he just crank it all the way up to 320 megahertz?
Let's go back to the highway analogy. Think of the channel width as the number of lanes on your highway.
Okay.
20 megahertz is a single-lane country road. 80 megahertz is a standard 4-lane highway. 1 in 60 or 320 is like a massive 16-lane superhighway.
Well, then I want the superhighway. Give me all 16 lanes.
You do want that if you were sitting in the same room as the router. But there's a massive trade-off. As you make the channel wider, the signal becomes way more susceptible to background noise and interference.
Why is that?
Because the router's power is finite. Spreading it across 16 lanes means each individual lane gets less power. It becomes quieter per lane. And it is much harder to keep 16 lanes of traffic organized than it is to keep 4 organized.
Especially when that traffic has to go through a floor and up a stairwell.
Exactly. So because he is on the second floor, pushing it to 160 or 320 might actually ruin his connection.
Really?
Yeah, the signal might degrade so much from the noise that packets just start getting lost constantly. He specifically calls 80 megahertz the sweet spot.
Because it balances things out.
Right. It balances high performance, 4 lanes of traffic with the actual physical range needed to get up the stairs and through the open door. If he tried 160, his link speed would probably drop or just become incredibly unstable.
That is such a crucial takeaway for setting up a home network. More isn't always better. It's about what's appropriate for the physical environment.
It rarely is about more. It's all about finding that balance.
Now we are talking about Wi-Fi 7 here. And there is a specific acronym that shows up in his data that flags this as next-gen tech, EHT.
EHT, extremely high throughput.
Not extremely humble throughput.
Definitely not.
Yeah.
When you see EHT in your connection stats, you know for a fact you were running on the 802.11 BB standard, Wi-Fi 7.
And under that EHT banner in the log, there are some really cryptic stats that look like a secret code.
Oh, yeah, the EHT parameters.
Yeah, I want to crack this code. We've got EHT MCS4, EHT NSS2, and EHT GI0.
Let's do it. Let's start with the first one, MCS. It stands for Modulation and Coding Scheme.
That sounds extremely complicated.
It sounds worse than it is. It is basically a measure of how complex the digital language is that the devices are speaking to each other. In Wi-Fi 7, this scale goes from 0 to 13.
Okay, and our source is sitting at a 4 out of 13. That seems pretty low. Is his connection bad?
It's not bad, it's just safe. Remember, he is on the second floor. The signal is good at negative 63 dBm, but it is not perfect. So the system has automatically chosen a complexity level of 4.
Qianmeng uses a driving analogy here that I really love. He says it's like driving 80 kilometers an hour in the rain instead of trying to go 120.
That is the perfect way to visualize it. If the router tried to use MCS 13, which is the most complex, fastest language, it would be exactly like driving a Ferrari at top speed on a wet road.
You're going to spin out?
You'd crash, you lose packets constantly. So the system smartly drops down to MCS 4 to ensure that the data actually arrives intact.
It prioritizes stability over raw theoretical speed.
Exactly. Health over hype.
Love that. Okay, what about NSS2?
That stands for number of spatial streams. This is where MIMO comes in, multiple input, multiple output. The 2 just means the device is using 2 antennas to send and receive separate data streams simultaneously.
So 2 hands are better than 1.
Exactly. It effectively doubles the capacity compared to a single stream. If he had a super high-end desktop card with 4 antennas sticking out the back, maybe he'd see NSS 4. But 2 is standard for almost all laptops and phones today.
Makes sense. And finally, the last one, EHTGI0. GI stands for guard interval, right?
Yes. And this is honestly one of my favorite concepts in radio physics. The guard interval is basically the breathing room between data bursts.
Breathing room.
Yeah, in radio transmission, if you send packets too close together, one after another, they can actually echo off the walls and collide with each other in the air.
Oh, wow. So the echo of packet A hits packet B.
Exactly. It's called multipath interference. So you need a tiny microscopic pause between packets to let those echoes die down before you send the next one.
And a 0 for the guard interval sounds like no pause at all.
A very, very short pause,
Yeah.
a short guard interval. It's technically about 0.8 microseconds.
That is incredibly short.
It is. The fact that it is set to 0 means the physical environment is clean enough that they don't need a long pause.
Yeah.
They can pack the data bursts incredibly tight against each other. It means the connection is running at high efficiency.
So to summarize this whole engine tuning section, we've got a 4-lane highway with the 80 megahertz.
Right.
We are driving at a safe speed for the rainy conditions with MCS4. We are using 2 lanes of traffic at once with NSS2, and we're leaving very little gap between the cars with GI0.
You've just described the physical layer of his Wi-Fi connection perfectly. You can actually visualize the data moving through the air when you break it down like that.
I feel like I finally understand what my router is actually doing all day, but there is one last section in the source material we need to touch on, the connection parameters.
Right.
The source describes this as the heartbeat of the network.
Yes. These are the underlying settings that determine how the router and the client stay in perfect sync, even when you aren't actively sending files or watching a video.
The first one he mentions is the beacon interval, and it's set to 100.
100 TUs. Time units.
What's a time unit in this context?
1 TU in Wi-Fi is exactly 1.024 milliseconds. So 100 TUs is roughly 102.4 milliseconds.
So that's roughly 10 times a second.
Yes, 10 times every single second your router sends out a pulse. It basically shouts, I'm here, I'm network X, here are my current settings.
It's the metronome that keeps the whole dance organized.
Exactly. Even if you aren't downloading anything, the airwaves around you are completely full of these beacons, just keeping rhythm.
And then tied to that there is the DTIM period. This part was super interesting because it involves a real-world trade-off between speed and battery life, which affects absolutely all of us.
Right. DTM stands for Delivery Traffic Indication Message.
Yeah.
Think of it as a wake-up call that gets attached to certain beacons. It tells your phone or laptop, hey, I have data waiting for you. Wake up and receive it.
And in the source's specific setup, this is set to 1.
Which means the client device checks every single beacon for that wake-up call.
So every 102 milliseconds, the client wakes up its radio and checks for mail.
Exactly.
That sounds absolutely exhausting for a battery.
It does use more power, yes,
Mm-hmm.
but it is fantastic for latency. If you are gaming online or you are on a Zoom call, you want that pack the exact millisecond it arrives at the router.
Yeah.
You don't want to wait.
Right. And what's the alternative if you care more about battery?
where you could log in and set the DTIM to 3, for example. Then the client only wakes up to check every third beacon.
So every 300 milliseconds.
Right. You save a bunch of battery life on your phone because the radio sleeps longer. But you introduce a tiny bit of lag because the data might just sit on the router waiting for your phone to wake up and ask for it.
It is fascinating that these tiny, tiny numbers, a 1 versus a 3, change the fundamental physical behavior of the device in your hand.
It really highlights the main point of all this. Wi-Fi isn't magic. It's just a highly configurable utility. It is a series of choices.
So bringing this all back to the big picture, we started with the universal frustration of dead zones and buffering. We looked at this deep dive into Wi-Fi 7 and MLO and terminal commands. What is the big takeaway for you from all this?
For me, it's about stopping the worship of big numbers.
Say more about that.
Well, we see Wi-Fi 7 on a box, and we immediately think more speed. But looking under the hood with Qian Meng, we see that the real victory of Wi-Fi 7 and MLO is actually management. It's about the router intelligently using both bands at once. It's about the device being smart enough to slow down to MCS4 to maintain stability instead of crashing. It's about consciously choosing an 80 megahertz channel instead of 160, just to ensure the signal gets through a floor.
So it's smart Wi-Fi, not just fast Wi-Fi.
Exactly. And by using tools like on Linux, we can actually see that reality. We stop treating the router like a magical black box that either works or doesn't.
Right.
And when you understand that 30 to 50% of your bandwidth is just overhead, it's management traffic, you stop being so angry that you aren't getting the full speed limit on your speed test. You finally understand the cost of doing business.
That concept of overhead really stuck with me reading through this.
Oh, yeah.
Yeah, the idea that to have a functioning system, whether it's a computer network or honestly even just a human conversation, you need a huge amount of management traffic.
It's true.
Just constant pinging. Did you hear me? Yes, I heard you. Are you ready for the next point? Yes, go ahead.
It's the tax we pay for connection.
It really is. And it makes me think, if 30 to 50% of a highly efficient, optimized computer network is just pure overhead, how much of our own mental bandwidth is spent on that?
That's a great question.
Right. Like how much of my day is just management traffic, scheduling, double-checking, clarifying, responding to the email about the meeting versus actual throughput, actual productivity.
That is a slightly frightening thought, honestly. I'd bet our human overhead is way higher than 50% most days.
Easily.
We're probably running at MCS2 most of the week.
Probably. Maybe we all just need a short guard interval to make our days a little more efficient.
Or maybe just an open door like the router on the ground floor.
True.
Sometimes the best solution is actually the simplest one, bouncing the signal up the stairs.
I like that much better. Open more doors. Thank you for diving deep with us today.
Always a pleasure to be here.
We'll catch you on the next one. Check your DTM settings, everyone. Bye.